Hello. Welcome, Mateo. It's nice to have you as a part of the DeSci Labs Journal Club.
Thanks. It's a pleasure to be here.
Always exciting. This is going to be the first iteration of the DeSci Labs Journal Club that we're putting up on YouTube, and we are thrilled to have such an incredible community member on board with us talking about some of your work in celestial mechanics. Definitely an interesting topic that quite a few folks are interested in. We also appreciate all of your work as an alpha tester and are excited to see what you put together through the DeSci Nodes platform. Just a little bit on DeSci Nodes before we get started. It is a cutting edge publication publishing application which allows you to put code and PDFs directly in line with each other. Based on a lot of your work around celestial mechanics, it seems like this particular application has been a pretty good fit for everything that you're trying to show.
Yeah, yeah, definitely. Thank you. So yeah, I'll start presenting right away. I'll try to be as general as possible on the technicalities of the paper. But yeah, this is a work I developed with Benjamin Boschmann from Telespazio, a space company in Germany. I was in AMS space. He was in Telespazio, but actually we were both working for the European Space Agency. And basically on the weekends we ended up developing this work that was presented at a conference last month, now that I'm speaking in August 2022. And so yeah, the work is about the stochastic generalization of a well-known problem in celestial mechanics called the three-body problem. And I've linked here my hero, which is Professor Shane Ross from Virginia Tech, which was actually at that conference, so that was nice. And in this video, he's introducing this well-known problem in celestial mechanics that's been investigated for a while, for a few centuries now. So as I said, this was in a conference. You can see that the conference is linked in this note on the PDF, and it was called Theory and Simulations in Celestial Mechanics. Yeah, in Pisa. So yeah, let's get started. I would say I would like to keep it more general, as I said, talking about dynamical systems in general, and thinking about how the deterministic assumption is often not good enough to model behavior in complex systems, in chaotic systems. And in fact, Zebehey, a famous scientist during the Apollo era in the US, wrote in 1982 this work called Is Celestial Mechanics Deterministic, which I've actually shared here. I think there's also the link to the paper. Yeah, probably this one is linked to the paper. And yeah, so the idea is that we cannot assume celestial mechanics dynamical systems to be deterministic. And I would say this goes well with other topics in dynamical system theory. For example, to give an example, the Nobel Prize in Physics 2020, Giorgio Parisi, gave a speech in which he said scientists did a really bad job in underlying the uncertainty in the outcome, in the modeling we're doing. And so this is also relevant, I think, for policy informing in the context of the pandemic. So being able to quantify uncertainty is really relevant in science as a whole. But yeah.
Matteo, sorry, can
Yeah.
you quickly tell us what it means for a system to be deterministic?
Yeah, a system is deterministic if you are able to construct a model that associate to a single state of the system in the future. To a single state in the present, only one possible single state in the future. So the law is a given, yeah, I guess there's no better non-formal way of saying it, like I said it. So today the configuration of nature is like this, and so we are able to. It's maybe related to information theory, like we can have access to all the informations that embedded into a model allow us to predict the state of the system in the future.
Gotcha. So, yeah, that makes perfect sense. Based on the current state today and the laws of nature that we know at this moment, in a deterministic system, we can directly predict what the system is going to look like at any given point in time.
Yep.
And part of what this deterministic problem is saying is that that's not exactly how celestial bodies work.
Yeah, Zebehay here said also in celestial mechanics this has to be done. I mean, we have experience of stochastic dynamical systems, like the context in which Brownian motion is well known, the 1905 paper by Einstein about the motion of a particle in a fluid field. So you have this thermal bath of all particles wiggling, and you have, I mean, and the evolution is kind of random. I mean, in principle, and this goes into the philosophical discussion about whether nature is deterministic or not, but in principle, the 1 million particles in the glass have a single deterministic state, and if you were able to measure all of them, and this is the Leibniz point of view, if you were able, if someone had access to all the informations in nature, you would be able to predict everything. So that's an example of a stochastic system. I mean, and even clearer is the stock market. I mean, we know the price of an asset is evolving in time, so it's a dynamical system. But I challenge people to predict the price of something in 6 years. You know, it's a tough problem. Even though in principle there should be all the info. I mean, I don't know. I don't want to go into free will, but you get the point that. It's a deep discussion, which was brought into celestial mechanics by Zebehay in this work, and since then a number of people tried to incorporate this perspective in celestial mechanics. I would say this is also a trend in classical mechanics in general. In fact, Zebehay wrote another paper 10 years later about the open question for the next millennium in celestial mechanics, something like that. And one of the points was the underlying of the use of statistical tools from statistical physics into classical mechanics and celestial mechanics. So there's kind of this big movement in culture, which I think is also related, to Ilya Prigogine, which is a Nobel Prize in chemistry from the 70s, which collaborated with Zebehay later on, and which inspired his reflection on this deep philosophical, assumption-like reasoning. But then, since on that many people built, and there've been these works in the last 20 years. They are not exhaustive, but I'm particularly inspired by this random walk in celestial mechanics by Bel Bruno, of which I recorded a conversation here in the link. And the same with Marian Gidea, both from Yeshiva University. I think Bel Bruno is also in another institution, but they work together. And they wrote these different papers attacking celestial mechanics, let's say, from a stochastic point of view. I won't go into the details of the mathematics, but you can do some assumptions about the nature of the probabilistic part of the system, and you get a way of modeling it, which has important consequence if you assume that the statistics is of a particular nature. So here I put Anito's lemma for kids, which I think is useful to understand all this fancy mathematics. Because of the nature of the Gaussian, so the classical, let's say, stochastic perturbation, the square of it, because the covariance of the Wiener process, which is this process here, is proportional to the time. You have that the square of the process is not zero, of the differential of the process, not zero, but it's t. So, I mean, at the end of the day, it comes out that if you do an expansion with respect to small quantities, you have to keep in mind that the square of the stochastic perturbation is proportional to time, and so you have a drift. You have a non-zero drift associated to a nonlinear function of a state with zero drift. Because, I mean, maybe even clearly if you have something that's whose mean is staying to 0 and the standard deviation is increasing, something like this.
Yeah.
When you consider the square of that object, you're gonna have a non-zero. The mean is gonna increase because all the values negative are gonna be shifted, mirrored on the positive side, and so you're gonna have something that goes like this, and because it's increasing only on the positive side, the mean is gonna move while this is increasing, and so you have a drift in the mean and also an increase in the standard deviation in time. And so this variation of the mean is important.
So I guess just a couple questions around that. Based on what you've said, my current understanding is that this theory states that things are always going to spread out. Chaos, chaos is always going to encourage things to move away from the mean and to disperse into whatever deviation fits a particular scenario. In the scenario you just described, what is the mean? I guess would be my first question.
Yeah. Yeah. So if I were picky, I would correct you saying it's not really, and which is what I'm doing, but it's not really chaoticity, it's stochasticity, which it's like a layered. You can think that stochasticity is our way of encoding an underlying chaotic scenario, and then chaos. You can argue that it's the manifestation of stochasticity. I mean, I don't know what's the starting point, but stochasticity is related to chaos, and but yeah, okay. Chaos leads to diffusion. Definitely, that's a fair statement, also formally. And in this case, what's the mean? The mean is that we are gonna focus on objects whose mean, in the deterministic case, is conserved. So if there were no probabilistic perturbation, there are objects which are constant. So like the orbit of the Earth around the Sun is always the same. Its energy is always the same. The angular momentum is always the same. In the three-body problem, there's a different quantity, but still you have this object that's conserved. And in the deterministic case, you're gonna have something still conserved. And but what we are showing here is that because of this drift in the mean, the energy is not simply gonna spread out, but also move on average.
Gotcha. Okay, thank you.
Okay. So this is a slide that I think it's important to discuss it, to underline the importance of the node and the possibility of updating a work. Because here we spent some time on reasoning about why previous work modeled the stochastic perturbation to be Gaussian, so to be well-behaving. I mean, it's the easiest way of modeling a random process, the most trivial one. We tried to show something numerically, but actually we're still not convinced, and we had a couple of questions about why we did this modeling. I mean, it's a modeling that starts from the assumption that the solar system is full of fluctuating density of objects. So there's like interplanetary dust, full of dust, that's gonna fluctuate. And so because the density is assumed to be constant in this model, in space, but not in time, so they're gonna fluctuate all in the same way everywhere, which is not a good assumption, I guess, which was made in previous works. We built on that, but we are actually gonna challenge this assumption. And so we have a note here that I hope in the future can link to an update of this work, saying, okay, here we did this, but actually there's a fork at this point. We're branching out of this work, and the reasoning keeps making sense here, but if you change this assumption, you're going to move to a different work.
And Matteo, if I can just quickly add on to a little bit of what you mean in terms of just adding on to this work, is there any way I can get you to open up the components or the composer menu in the node?
Right, yes. So here on the right, there's the list of objects that compose the node, which is not just the PDF, but also, actually, I didn't mention, but there's also the code here, and which I think has, I could show you this code, which generalizes an already available open source code which only applies to one-dimensional systems. Here we have a code that applies this transformation to n-dimensional systems, general systems. I think there are some assumptions about the transformation, but the function that's useful even in, I don't know, outside celestial mechanics is here, and so people reading it can access it. Beside this, there are some codes written in Julia. I'm a big fan of the Julia language, and yeah, and here's the code. So let's say in the future I'd like to add here another paper and then add on top of this slide here, yeah, this one, like a link to this title saying new branch challenging this assumption. And yeah, I can use LaTeX and Markdown. So what if the reference statistics, okay, you get the point, it's not Gaussian. See here, and I'm gonna use Markdown to link this work. Okay, kind of makes sense. Sounds good. Okay, then I save it, and this is gonna stay here, and it's gonna populate my node as all the other nodes I have here.
And I think just one quick thing to add on to that, it's always interesting to see the history of a node and to understand how it evolves. So the way that we've set up this particular application is such that, and it will be enabled in the near future, this is one of the features we have coming soon, is such that whenever you make a change to your node, whenever you click the save button up top, commit changes on chain, the history of that node adds another iteration. So if there were information that were there previously, and you actually wanted to challenge that, you could add an annotation. You could change PDF, whatever the actual change needs to be, and can show people in real time that your thinking around this particular concept has changed. And they can actually work to kind of track some of the way that your thinking has changed. So definitely a neat one that we're excited to enable in the future.
Well, and the old one is going to stay. I mean, is the IPFS technology, what's the role of IPFS in all this?
Yeah, so IPFS is a backend content addressed file storage system that basically allows information to be permanent and immutable on chain. So one of the things that we can do is save the old version of the manuscript. So anytime that a change is made to a specific node, the components that have not changed, they stay the same. Nothing happens, no additional copies are stored on IPFS. But since it's a content addressable system, what that means is that we are indexing information based on the content stored in a file, not based on some arbitrary file path. So if you change the PDF with additional information, if you add an annotation on top of it, those specific changes are linked as a part of the node. And our backend will go through and actually kind of check to see what changes have been made. So previous iterations of the node are available. Your current thinking can also be shown. So it's a great way to show kind of the history of this piece of knowledge.
Right.
So yeah, sorry, just wanted to mention
that. I wanted to ask why specifically IPFS now that I'm using it.
Yeah.
But yeah, so the hope is that we can branch out. Yeah, I was referencing Git, and I guess IPFS is compatible with that in saying, yeah, there are going to be two branches of the same project, which is Stochastic Celestial Mechanics. And then you have two papers which come out on the other side.
Okay. So
but yeah,
I think that is a solid understanding of deterministic systems and how stochastic methods should be applied based on variables in space that can affect bodies. I think I'm good.
Yeah, okay. Yeah, so we can jump into the two-body problem, the stochastic two-body problem, which is, I mean, the two-body problem is the easy one. We have the Earth rotating around the sun, and it's gonna go around an ellipse, and it's gonna stay there forever. That's the model. Kepler, Tycho Brahe, Galileo, Newton, all these people arrived at this model. But then someone, I don't know when this was introduced, I think the Sharma-Parthasarathi work around 2005, something like this, proposed this model for a stochastically perturbed two-body problem. And so here we're not inventing anything, we're just rederiving it, showing the explicit evolution in time of the energy, which is the quantity I was saying it's conserved in the deterministic case. Because in the deterministic case, yeah, I mean, you can work out the equations of motion and arrive at this thing being a constant. But because we're considering a stochastic perturbation, this is going to be equal to this thing here, which is not constant, but it's in fact evolving in time. And in particular, with respect to time, this is a positive object, which is the thing I was saying before. So you have the Gaussian, you flipped it, and so you have all objects. So let's say R is just getting wider because it's squared and all these other things are squared, then this thing is gonna be positive. And so there's gonna be a mean. Well, here we have the part associated to the uncertainty, the diffusion it's called. So there's drift and diffusion. While angular momentum, which is another object conserved, if you do these transformations, we arrive at seeing that actually here the mean is conserved. So the mean of the angular momentum stays at the value which would be conserved in the deterministic case, while the uncertainty is increasing in time. And so we showed this numerically. In the stochastic case, you see that the orbit is kind of changing. We are still kind of on an ellipse, but we are filling a region because the radius is changing and the angle is changing. In the deterministic case, instead, we are still revolving around forever on this. And these quantities, okay, here, because numerical error plays a role in the integration, you have this thing, which is looking decreasing, but actually the number, you see, it's always the same. So we are dealing with numerical precision error. Well, here, you see that this looks like Bitcoin, I don't know, the stock market, Tesla here. And and you see the evolution of a stochastic quantity with all this wiggling on it. And here you cannot see the difference of what I said before, like you cannot distinguish qualitatively between the behavior of the energy and the angular momentum. But if you actually consider an ensemble, a Monte Carlo simulation it's called, so you model many, many possible futures. And so you say, okay, stochasticity plays a role because in 2 days, the bus could be 2 minutes early, on time, 1 minute late. And so to have an overall description of the system, you say what's going to happen in a week if the bus arrives here, if the bus arrives here and arrives here. And so you do many, many simulations. Here, in principle, you would need infinite, but you do many and you arrive at something reasonable. And you see that with already a few simulations, the energy is going up, the mean, and it's spreading out. So the more time goes by in the future, the more you're uncertain about what the value of the energy is going to be, which makes sense. While for the angular momentum, again, because of the numerical precision, but also because of the limiting number of it's called realizations. So the future can realize in different ways. So you consider different realization, and then you look at the behavior of the quantity, and then you put them all together. The mean is kind of constant here, because we're not considering an infinite number is not really constant. If we were to do that, we know that's going to be constant from the equations. So yeah, this is all for the two-body problem. Then we said, okay, let's do the same for the three-body problem, which is a super cool system in celestial mechanics. So I won't bother you here with the details, but what we wanted to show is, building on Belbruno, is that this work could give a causal modeling of the formation of the moon. So Belbruno argues that there's an object living in an equilibrium point that, because in the nominal case there are constants, it's going to stay there forever. In the stochastically perturbed case, you have something staying at the, like, on an equilibrium. Yeah, let's think of a ball in a cup, but it's shaking. And because the shaking, it's influencing it not only in diffusion but also in drift, the body, as time goes by, it's gonna move even on average from that point. And so you see that at first it goes like this, then it keeps going away even more, and this is the object that's supposed to be constant on the left.
Okay.
And then you keep going, you form what's called an horseshoe trajectory. This thing is an horseshoe trajectory, which connects two different equilibria, L4 and L5, 2 points here in this plane. But eventually, you're gonna break out of this horseshoe orbit and you're gonna intersect the blue marble, which is home. And because we are assuming this is the sun and this is the Earth. And so there's gonna be a non-zero probability of this object to impact the Earth. And so I don't know if you know, but the most probable, I mean, the most people are thinking that the moon formed because a Mars-sized object impacted the proto-Earth, and from the impact, a cloud of debris formed, and they coalesced. They attracted together all this debris, and the moon came out. I think they say this because the rocks of the moon are similar to the surface of the Earth or the interior. I don't remember, but there's a reasoning for why this could make sense. And here we're saying, okay, but where did this object come from? Maybe it coalesced in an equilibrium point, but then because there was still a lot of dust, this thing was excited. Maybe it was also impacted directly by objects. And it went away from the equilibrium and started increasing its energy until it impacted the Earth.
So, Matteo, in this three-body problem, what are the three bodies that you're considering? Would it be the Earth, the Moon, and the Sun?
No, the Moon is not there yet. So it's the Mars-sized object, which is the thing starting here, which is the thing tracing out the blue line. The Earth is the blue one on the right, and the Sun is the yellow in the center. And the Sun is staying at 0, 0 in the origin of the system because it's much bigger than the Earth. And this has also influence on the gravity of the gravity. But yeah, I won't bother with that. But yeah, the system is Sun, Earth, small object, which is not really small, but smaller, Mars-sized object.
In the scope of the solar system, it's small.
Yeah.
Okay, that's it.
Yeah.
Thank you.
And so here we show this this weird equation that says how this thing, which is constant in the deterministic case, is evolving, and it's going down, which means that the energy is going up on average, and also we are more and more unsure about where it's going to be in the future. The goal of this work was the origin of the moon, also the formation of potentially hazardous asteroids. So there are once in a while we discover asteroids that could impact the Earth, and I mean, we kind of know where they're coming from, but people are looking into possible ways in which they come to be hazardous. And one way could be that they are staying at they're called the Trojan population, and they're staying in this around this equilibria, and maybe they escape this condition because there are so many that there's still a stochastic perturbation playing a role, which excites them on average and makes them escape and become dangerous. So I guess we cannot do anything about that, but it's a first step. And here a point about the technology is that actually we arrived at a conclusion that challenged one of the assumptions we had made at the beginning, another one, which is I guess a good thing. But we were expecting to see stochastic resonance, which is this behavior that again Giorgio Parisi, which I've been following after the Nobel Prize winning, he built with colleagues a model for climate in which he introduced the stochastic resonance, in which basically you have two equilibria in your deterministic part of the field, but then there's also someone playing with it randomly, and so you have a ball staying here and you're annoying it. But because there's also this behavior that you can go away on average, you're gonna have moments in which the random kicks a line and make you jump over the hill and you arrive at this other part, and then the same thing happens, and so you're gonna have this thing that goes like this, and so you're wiggling around one equilibrium, then you go on the other one, you stay around that for a while, then you go again, and you have this critical transitions, they're called. You can go from one equilibrium to another due to even really small kicks. If they align together in an improbable way, but not impossible, you're gonna have this behavior.
Exclusively based on randomness.
Yeah, yeah.
Okay, that's kind of cool. I know it's I could definitely see where it would be possible. I can only imagine how long it would take for everything to align in that kind of situation. But yeah, that's cool.
Yeah, I don't know the probabilistic in that case, but they were doing this for climate, and I think the kicks were due to the activity of the sun, which is not perfect. Let's say the flux is not constant, but the sun is doing crazy things, and there's
Okay.
I mean, if you look at the activity of the sun, it's like the stock market again, even though there's a big waving behavior. And I don't know what it means to be in different equilibria, but maybe the temperature of the atmosphere changes, and this is related to climate change, climate science. So yeah, we were hoping to find this here because there is this scenario in which, I mean, if you look at the figure here, you have two equilibria, and maybe the horseshoe trajectory is the best one to show this. You have two equilibria here, and you jump from one to the other. Okay, this is not a one-dimensional as in the Parisi case, but still, if you think about going around this horseshoe, you have a line that's connecting two equilibria. And so we were hoping to see something that was staying around L4, wiggling a bit, then doing a big jump, go around L5, stay there again, and jump again, and go like this. But actually, I mean, once we did the work, it was trivial to think, okay, this doesn't make sense, because since the energy on average is drifting, we're gonna have a moment in which we break out from this stochastic resonance. So even between the beginning of the excitation to the escape, there's not gonna be a period in which I'm going like this. But that's, I mean, there were an overstatement. I mean, we were claiming two things to happen while one is contradictory with the other, and we didn't notice this at the beginning. So I was saying this to say, if we could update this work, that would be cool. I mean, to add a version 2 using the node.
Gotcha.
So
I can see how those two things would be at odds with each other. So what you're saying is that the energy of a particular body in the system is going down, but that we need this energy to fuel randomness, which is how you would see the energy kick out into a new equilibrium or orbit. So with the energy going down and then dependence on energy for randomness to actually kick it out into a new equilibrium, those two things are at odds with each other.
Yeah, because one is pushing for the mean to change on average, and one is just pushing for randomness to hope to be aligned. And actually, we have seen, I think we don't have the equations of motion here. Oh yes, we have. Basically, if we were to change this matrix, so to for example put 0 here and 0 here, I'm pretty sure stochastic resonance is gonna happen, but it's not gonna escape. It's not gonna impact the Earth, so it's gonna go like this forever. I mean, I'm not sure, but I'm pretty sure if we remove some elements from here, the consequence is that I'll have to think about this, but I think there are ways to change the model so that stochastic resonance appears. But then that's even less physically based than the model we have now. So it's just it would be a nice experiment, but even less in touch with nature as this one. But maybe still interesting. I mean, it could be another branch, yet another branch.
Yeah, why not?
Yeah. So actually, you asked what's the probability of this phenomena to happen, and we didn't quantify this, but we were hoping to do this in the future, like okay, given a stochastic system, what's the probability of an object escaping? Because one thing we didn't say here is that if you have a super highly eccentric orbit here, which is super big, let's say going to infinity, almost infinity. I mean, okay, it's a model, but you can have an increase of the energy that makes you arrive at what's called the escape velocity. And if you arrive there, you're never gonna orbit the object again. So let's say there's a comet coming by the sun into a highly elliptical orbit, but still on orbit. If there's a stochastic perturbation while it's passing by, which gets it excited, then the energy goes positive, and then when it goes away, it's not gonna come back. So that could be a cool thing to look into. What's the probability of that happening?
Okay, very cool.
And then, what's the probability of this thing actually impacting the Earth? We didn't compute this, and we didn't even put physical-based numbers, so we don't know what's this number. Then this one, it's a fancy mathematical one, which I don't even know enough about to discuss. And actually, the last one we did it a couple of weeks ago. We presented a work on this. So it's gonna be cool then to put them together and try to have a generalized chaos description of a stochastically perturbed dynamical system. That's gonna help us also answer questions about the stability of the solar system. Because I mean, the big claim of this line of thought is people in the 700s thought the solar system is stable. Then works in the 20th century said actually it's chaotic, and we have a way of measuring how chaotic it is and when Mercury is gonna impact with the Earth. And here we are saying, well, if we're considering millions of years in the future, maybe even really small perturbations, if they're stochastic, can play a role and can change the stability time of, can probably reduce, which is a bad news for us. But I guess we're gonna be multiplanetary by the time that happens. That's gonna change the time in which we can expect the system to remain stable. So that's kind of what we're looking into. And this is it.
Okay, that is fascinating. What got you into this field in the first place? Just out of curiosity.
Good question. I don't know. I mean, math forever. Celestial mechanics. My professor, probably my bachelor professor from Pisa, actually.
Okay.
Giovanni Gronchi. Which presented actually the three-body problem. There was a specific lecture about, here we're dealing with two, but what happens if you introduce a third one? Yeah, things get tricky. And that was my exit door from engineering to celestial mechanics, to applied mathematics, which I guess is what I've been doing here. So yeah, professors, definitely, in my experience, role model are driving my choices. Yeah.
Okay. Very cool. I had a couple of those throughout my mechanical engineering undergraduate who really pushed me towards, actually a lot of it was based on chaos theory, vibrations, everything around that in my mechanical engineering. And that was one I actually considered going into a doctorate in for a little while. It would have been interesting. But yeah, no, that's so. I guess how long did it take you to create this entire piece of work? And what were the biggest challenges in doing so?
The actual work, or from the conference to the node, you mean?
The actual work.
Yeah, the actual work. Yeah, it's difficult to say because I mean, even in 2020, I've been reading works that made me think. Okay, let's think about this three-body problem with stochastic perturbation. So a big, I don't know. In the background of my mind, things have been going on for 1 year, and then I don't know when I found the right moment, I was able to clear some space and say, okay, let's investigate this thing. And then we suffered a lot in implementing the script I showed. That's why I was showing it, because it was a pain in the neck to understand it at least. Then once we implemented it, it was easy then to do all the transformations, but it took, I don't know. The thing is also we were all working like 3 hours per week in 2, so 1 hour and a half on average, and we took 4 months, 6 months, I don't know, something like that. So yeah.
What language is that written in, by the way? And is there a link to the GitHub that people can have?
Yeah, the GitHub, I'm not sure if you can access it from here, but I'll be sure to put the link in the description of the video. It's my public repo. It's public. The repo is public, and it's in my GitHub account. And the language is that for that one we use Python, but in general we are using Julia because it has really cool. For stochastic dynamical systems, it has a lot of tools. That also maybe this is worth underlying. We spent a lot of time trying to find the good numerical scheme that would have allowed us to model these things. Then we said, okay, let's give up. Let's use the ones they have already implemented. But actually, yeah, there's I think linked in my GitHub there are a few GitHub issues on the diffq repository, which is the Julia language repository,
right?
Which I could link. I mean, are inside the GitHub, but yeah, one day when we actually write a proper paper instead of a presentation on this, and we argue for the numerical scheme, we're probably using the node. We're probably gonna be able to document the struggle.
It will be interesting to see that throughout a node in history. So I guess another question I have for you. At DeSci Labs, one of the things that we really try to push for is reproducible and replicable science. So what are the steps that someone would have to take to reproduce this experiment? And can you just quickly walk me through that?
Right. Yeah. Okay. Stochasticity has a big problem in reproducibility. I mean, we can fix that by initializing. There's a random number generator that's basically the computer is kind of throwing a dice in the background, and then it's starting to simulate a stochastic process. We didn't do the manual setup of the initial number of the dice throw, so every time one person runs this experiment, it's going to get a different result. Having said that, actually people can start from the paper and understand stochastic calculus. Once they've done that, they have the code for this modeling and for this energy propagation, and in particular this is in the stochastic Sharma two-body problem.julia. And here there's everything. Basically there's the dynamical system. This is the deterministic one, which is showing the comparison between what's going on the left of the plot versus on the right. Here's the stochastic perturbation, which is state dependent. Here's the numerical integration, the plots, blah blah blah. And then here there's the ensemble analysis, so the Monte Carlo. So people can simply run this script and they're gonna get out of it a few plots that are populating the presentation. Not exactly the same as I said, because for example this one could look different, but this one should look fairly similar because this is taking into account as I said, all the possible realization of the future. So I'm considering all the possible dices. That's a way of thinking about it.
I mean, the whole paper is based on randomness, so
yeah. So
the graphs may not come out identically, but at the very least, a lot of your underlying methods are there.
Yeah.
And
as I said, yeah, people should also. I mean, one day when we aim at making this reproducible, and for example, try to associate a figure to a specific part of the script. We need to add this seed. It's called a seed, a random seed, which is generating the process, so that every time you run this, you're going to get the exact same figure. Which sometimes it's important.
Another question for you here. Are there different ways that you would have modeled this experiment or conducted this experiment based on the knowledge that I guess, more advanced tool sets for publishing and reproducibility are available.
Right. Yeah, so I think, yes, all the struggle on Ito's lemma would have gone away because, I mean, we would have known that there was the need to go to a higher generalizability. So even from the outside, there would have been the incentive to make something generalizable. And actually, we spent a lot of time to do the same thing by hand without automating it, without coding it. Try to understand it. I guess a part of it was necessary, but a part was just a waste of resources. If we knew that this was supposed to be integrated in the work, would have been more. We would have gone for the big. I don't know what to say. The big product, the big outcome, instead of starting from the case study, the specific with the specific assumptions. We would add an incentive to go into generalizability. So I think that would have been better. Beside that, I think there are cool ways to show these results in an animation style. So there are already, for example, online conferences that are recorded and you can show animations. But I think this would really simplify things. I mean, think about the outcome not as the PDF, but me coding, changing parameters, showing the results, discussing, okay, for example, the thing I said before, let's put here at 0. Can we find a stochastic resonance? If this was interactive enough and I had done that in advance, we would have got another paper out in 30 seconds, you know. So that's really, I mean, it's making things easier for sure for other people to then get on track with what you've done and to let them avoid reinventing the wheel. But even more, I think personally, you get to build on top of yourself. You get to challenge assumptions, take a look at other avenues much more easily, and then at the end, the outcome is much more powerful, much more general. As I said, yeah, generalizability, I think it's more important to me than reproducibility here, even though they're both present.
Absolutely. That would be absolutely incredible if you were able to go in and just change the parameters live in code and have that update accordingly. Living, breathing, interactive science would be fantastic.
Yeah.
And that is what we're working towards.
Nice.
Yeah. Well, do you have any other thoughts around that you want to share about the work that you've done around the Nodes platform? Just anything in general?
Yeah, I hope this becomes something, changes things in a major way. And I see it possible, so I hope it happens.
And we hope so too. That's why we're building this, is because it actually can make science reproducible, interactive, generalizable. We can have a lot of positive impact here. So yes, absolutely. And just for anyone else who's listening, we will make sure that the link to the demo for this DeSci Nodes application with the full feature set that we plan to be enabling is posted in the video link below. We'll also send information of where you can go to see the sign up link for DeSci Nodes. So if you want to come and be one of the alpha testers, or if you want to participate in our open beta, more than welcome to, and we would love to have you. We'll be having many more journal clubs after this and are excited for each of them. And Matteo, as you're going to be kind of the host of each of those journal clubs, I'm excited to see some of what comes up.
Yeah. Let's see. We're already arranging the next one, so fingers crossed.
Alrighty.
Okay. Thank you very much for letting me present this. It was a pleasure.
Thank you, Matteo. It really was.